Hello everyone and welcome to our YouTube channel where we will be talking about thermodynamics, specifically about equilibrium for processes with phase changes. Today, we will give you a brief introduction to the wide subject of thermodynamics and explain fundamental concepts that you will need to know in order to understand the next videos. Let us go back in time and see how thermodynamics, the study of heat transfer, started. Even before engines and machines were invented, humans understood how heat was transferred from objects to cold ones. Everyone knew that a freshly baked loaf of bread would cool down if left outside. Moreover, everyone knew that some processes could not be reversed. A vase that fell and broke can never go back to its original state. While these things might appear obvious, the reason for their behavior lies in thermodynamics. Of course, back then nobody knew that. It wasn't until 1850 when Rudolf Clausius and William Thomson studied two principles of thermodynamics which evolved into what we know as first and second law of thermodynamics. Later on, both zeroth and third laws were described. In order to make sure that you and I will make it through this thermodynamic equilibrium course, let us start by revising fundamental concepts among other important issues such as the laws of thermodynamics.
When we talk about a system, we are referring to a specific region in the universe that we are going to concentrate in to study. This system has a boundary, a physical or imaginary separation from the rest of the universe. Systems can either be open, closed, or isolated. In an open system, energy and mass are transferred to or from two surroundings. A water heater, like the one in your house, is an example of an open system because water is flowing in and out of it, and heat is being transferred to the cold water. In a closed system, energy is transferred but mass is not. An airtight container with coffee inside is a closed system because heat is transferring from the hot liquid to the surroundings, but the coffee and air inside are not escaping the boundary, the container. If the container were perfectly insulated to prevent the coffee from getting cold, the system will be isolated. No energy or mass transfer will happen. The first law of thermodynamics is also known as the law of energy conservation and states that during a process, energy can be changed from one form into another but will always remain constant. For a closed system, it can be written as where Q is heat, W is work, then we have internal energy, kinetic energy, and potential energy. At this point, we must make an important distinction between heat and work. From a molecular point of view, heat is an energy transfer that causes thermal motion in the particles of the surroundings, whereas work is an energy transfer that causes an organized motion of the particles in the surroundings. For an open system, we must take in account the mass of volumetric flow. That means that in an open system, we change internal energy and we add dots, which means flow. The second law of thermodynamics, which we will discuss more in depth in our next video, tells us that processes will always move towards a state of rate disorder or entropy, and that during a process where heat is converted to work, for example in an engine, some of the heat will inevitably be lost to the surroundings. In simple terms, it can be written as this, where S is entropy, a measurement of disorder. Related to this concept is the third law of thermodynamics, which states that when the entropy of a system is close to zero, its temperature is also approaching absolute zero in Kelvin degrees. Finally, the zeroth law of thermodynamics talks about equilibrium and states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other.
The effects of thermodynamics can be experienced at all times on a daily basis. You may even know more about it than you think. For example, picture yourself holding a ball above your head. You know from experience that the moment you let go of it, it will fall right to the ground, right? And depending on the material it is made out of, maybe even bounce a little. Let's examine what is going on here. When the ball is stationary at any given height, it has energy. This energy, which is related to gravity, is known as potential energy, and it's calculated through this equation, where m is the mass of the ball in kilograms, g is the acceleration of gravity in meters per square second, and h is the height in meters. If we were to let go of the ball, the energy it possesses would transform to kinetic energy, which is related to movement and is calculated through this equation, where m is the mass of the ball in kilograms and v is the speed of the object in meters per second. The ball will eventually get to the ground, a height equal to 0, and its energy will once again suffer a transformation due to impact, now into sound and heat to the nearby particles and eventually completely dissipate to the surroundings. This example helps understand a little bit better the concept of the first law of thermodynamics, but it also can be related to the second law of thermodynamics. Why did the ball fall? Why did things happen in a way and not the opposite? If a ball was on the ground, could it randomly make its way to my hand? Well, this has to do with the energy a system requires to go from one state to another. The moment one lets go of the ball, the system needs no additional work to go right to the ground. But a ball in the ground does not have the energy needed to travel all the way back up. This is explained with entropy, which is sometimes referred to as a measure of disorder. In relation with our example, the energy in the initial state of the ball is stored within the ball, where the energy in the final state is everywhere as it dissipated to the surrounding particles, in the air and in the ground, as it hits. Therefore, there is more disorder in the final state, which is the natural way of things to happen. Entropy in the universe will tend to increase over time. A system always goes to the higher entropy state.
Now it is time to review what we've learned so far with a problem. Let's imagine we have a sealed 2-liter tank filled with a water vapor mixture at a temperature of 120 degrees Celsius and a quality of 0.5. We need this mixture to be at a temperature of 130 degrees Celsius, and we want to know how much heat we need to transfer to the water for that to happen. In the initial state, the internal energy of the mixture is 1516.25 kilojoules over kilogram, and in the final state, it is 1876.29 kilojoules over kilogram. The specific volume will remain constant and equal to 0.446195 cubic meters over kilogram. From the first law of thermodynamics, we know that the heat is equal to the change in internal energy, since there is no work involved and no change in kinetic or potential energy. We also know that this is a closed system. The change in internal energy is calculated as the mass multiplied by the change in internal energy. So the internal energy of the state 2 minus the internal energy of the state 1. We can calculate the mass of the water as the volume over the specific volume, which gives us 4.48 times 10 to the minus 3 kilograms of water. Substituting this with the first law of thermodynamics, we get 1.61 kilojoules that will be transferred to the water for the temperature to rise.
Now, summarizing everything we have said, you have to remember that a system is a part of the universe that can be either open, closed, or isolated. In an open system, heat and mass can be transferred, whereas in a closed system, only energy is transferred. In an isolated system, no energy or mass are being transferred. Now, the laws of thermodynamics. The first one is about energy conservation. It says that energy can be transformed from one form to another, but can never be created nor destroyed. The third law dictates that the entropy of a system approaches a constant value as its temperature approaches absolute zero. And last, but definitely not least, the zeroth law of thermodynamics. It states that if two systems are each in a thermal equilibrium with a third system, then they are in thermal equilibrium with each other.
To test what have been learned so far, here's a series of questions related to today's review. Question number 1. What does the thermodynamics study? A. Matter and its motion and behavior throughout space and time. B. The mechanics of fluids, liquids, gases, and plasmas, and the forces of them. C. Heat transfer. The correct answer is C. heat transfer. Question number 2. What are the characteristics of an open system? A. Both matter and energy exchange are possible. B. Nor matter or energy are exchanged. C. Only matter exchange is possible. If you choose letter A, you are right. Remember that both matter and energy exchange occur only in open systems. Question number 3. Which of the laws of thermodynamics describes energy conservation? A. Zeroth. B. First. C. Third. The first law of thermodynamics says energy can be transformed from another, but can be neither created nor destroyed. Therefore, letter B is the right answer. Question number 4. Which of the laws of thermodynamics describes the tendency of a process to move towards a state of greater disorder? A. Second. B. Third. C. Zeroth. Since the zeroth law describes thermal equilibrium and the third law is concerned with the behavior of a system as its temperature approaches to absolute zero, the right answer is letter A.